Hello, in this video we'll discuss about some miscellaneous properties of Fourier transform. So we have the first property as time differentiation property. So the first statement will keep as it is. If we have x of t is Fourier transform of x of j omega. Now we have to differentiate in time domain. So we'll differentiate input signal d by dt of x of t and its Fourier transform will be j omega into x of j omega. Now let us prove this property, and to prove this property we have to differentiate input signal x of t. So for that case we'll use the second pair or second equation of Fourier transform, that is inverse Fourier transform x of t will be equal to 1 upon 2 pi integration over the range, suppose minus to plus infinity. This is x of j omega e raised to j omega t into d omega. Now we'll differentiate on both the sides with respect to t. So this equation holds d by dt x of t is equals to 1 upon 2 pi integration. This is d by dt x j omega e raised to j omega t into d omega. As far as differential term is there, this x of j omega becomes constant, and the only term that we can differentiate is exponential. And the differentiation of exponential function, we know it. I can put this value as it is, x of j omega into e raised to j omega t. So differentiation of this equation holds j omega into d omega. E raised to theta's differentiation will be e raised to theta into theta's integration and differentiation is 1. I can take j omega outside, so this equation remains 1 upon 2 pi integration x j omega into e raised to j omega t into d omega. Now this entire term we can converge to one term, that is x of j omega, because we are integrating from minus to plus infinity, and if I collect all the sample values we get this equation. So this property is called as time differentiation property. Now if it is a time differentiation property, let us come across frequency differentiation. We have the first statement as xt's Fourier transform is x of j omega. Then now we have to differentiate in frequency domain, so this holds d by d omega x of j omega. Now again we'll assume that we don't know anything what will be the result of it. We know only we have to differentiate with respect to omega. So for that case we'll use an equation that is called as Fourier transform equation, which is x of j omega is equals to integration xt into e raised to minus j omega t into dt. Now let us differentiate on both the sides with respect to omega. We'll get this term d by d omega x of j omega is equals to integration x of t as it is. Now differentiation of this with respect to omega will be e raised to minus j omega t into minus j t dt, because differentiation of omega will be 1. Now if it is there, we'll take jt outside. This is minus jt. This is our integration xt j omega t into dt. Now this entire term again converges to a single unit, that is x of t. This I can write minus jt into x of t. This side d by d omega x of j omega. Now here we have minus j, so if I multiply both the side with j, we'll get this term as j into d by d omega x of j omega will be equal to minus j square t into x of t. Now minus j square, that is minus I square value will be plus 1. Therefore this equation becomes t into x of t is equal to j into d by d omega of x of j omega. This property is called as frequency differentiation property. Let us come across the statement. So LHS we can write as T into x of t, provided that this is now multiplied with j. So this will be second property, which is called as frequency differentiation property. Let us come across another important property, which is known as convolution property. Now here we have this particular function. The statement is convolution of two signals in time domain becomes multiplication in frequency domain. Remember, quite important property, convolution in time domain is always equals to its multiplication in frequency domain, and therefore it is always preferred to switch from time domain into the frequency domain. In order to prove this property, we use the same set of equation as Fourier transform of x of t convolved with y of t is, we have that equation as integration x of t, convolution sign will keep as it is, into e raised to minus j omega t into dt. Now we'll replace this convolution sign with the convolution integral term. We'll use the formula from linear time invariant system, which is integration of x of tau into y of t minus tau into d tau. Now this entire term as it is, e raised to minus j omega t into dt. Now in order to simplify this set of equation, we'll merely concentrate on this term, that is y of t minus tau. So for that case, I am simply rearranging the term integration x of tau into integration, we'll keep y of t minus tau e raised to minus j omega t dt, and the last function as d tau, because here x of tau, so it should be d of t. Now let us put this value. Let t minus tau is equals to m, so our tau becomes equals to, or simply t becomes equals to m plus tau, and dt we can write is equals to tm. Now we'll put all these values in the entire equation. This is integration x tau, this is again an integration with respect to m. Now this will be y of m into e raised to minus j omega. Instead of t, I can put this value as m plus tau dm into d tau. Now just we'll simplify the terms. X of tau with respect to tau, y of m with respect to m. This holds integration x of tau e raised to minus j omega tau d tau, another integration as y of m e raised to minus j omega m into dm. Now this is an equation for x of j omega, and this is for y of j omega. They are multiplied with each other, so we'll get the answer as x of j omega multiplied with y of j omega. So this is known as convolution in time domain property. Now let us come across the next property as multiplication property. Now here we have to multiply in time domain and its result as convolution in frequency domain. So for that case, again in order to prove this one, we'll use the same formula, Fourier transform of this function, which is equals to integration x of t into y of t. This is multiplied with e raised to minus j omega t into dt. Now remember the step. In the next step, we'll look after the term which is required in RHS. We need 1 by 2 pi. So 1 by 2 pi we have to go for inverse Fourier transform. So either x of t or y of t should be represented in a form of its inverse Fourier transform. So here I am treating y of t as taking inverse Fourier transform of y of t, probably y of j omega we can call. So this is integration x of t as it is. Now instead of y of t we'll write integration 1 by 2 pi. This term will get y of j omega e raised to j omega. Now if I put t in both the cases, it may be possible that we'll get some different values.